Hello everyone, welcome to my YouTube channel. I am Koshik and I am excited to share with you my presentation for college. Today I'll be delving into graphs and networks, so make sure to stick around to learn something new. Don't forget to like, share, comment and subscribe to stay updated with my latest content. Now let's get started. Introduction to graphs and networks. Explore the fascinating world of graphs and networks, where interconnected nodes and edges reveal intricate patterns in data, society, and the natural world. Discover how these powerful mathematical models provide insights into complex systems and drive innovative solutions. Firstly, let's look let's look at the graph theory fundamentals. There are four graph theory fundamentals: graph and nodes, graph properties, graph algorithms, real world applications. Firstly, graph and nodes. Graphs are mathematical structures composed of nodes. They are also called as vertices connected by edges. Understanding the relationship between these fundamental building blocks is key to graph theory. Graph properties. Graphs can exhibit properties like connectivity, weight, direction, and more. Analyzing these properties reveals important insights about the networks they represent. Graph algorithms. Specialized algorithms like Dijkstra's and Kruskal's are used to solve fundamental graph problems like shortest path and minimum spanning tree. Mastering these algorithms is crucial. Real world applications. Graphs have widespread applications in fields like social networks, transport, and computer science. Understanding graph theory is essential for modeling and solving complex and interconnected problems. Vertices and edges. Graphs are mathematical structures composed of vertices, they are also called as nodes, and edges, they are also called as links or connections. Vertices represents the fundamental elements or entities in the graph, while edges represent the relationships or interconnections between them. Vertices can be labeled with unique identifiers such as numbers or text and can have associated attributes or properties. Edges connect pairs of vertices representing a connection or relationship between them. Edges can be directed, indicated in a one-way relationship, or undirected, or it can be indicating a bidirectional relationship. Directed and undirected graphs. Graphs can be classified as either directed or undirected. In a directed graph, the edges have a specific direction indicated by arrows. In undirected graphs, have edges without a defined direction representing a symmetric relationship between the connected nodes. The choice between directed and undirected graphs depends on the nature of the connections in the problem domain. Directed graphs are useful for modeling one-way relationships, while undirected graphs capture mutual and reciprocal connections. Graph transversal algorithms. There are three methods in the following graph transversal algorithms. DFS, depth first search. DFS explores a graph by following one path as far as possible before backtracking. It's efficient for finding connected components and detecting cycles. Secondly, BFS, breadth first search. BFS explores a graph by level, visiting all neighboring nodes before moving to nodes further away. Useful for finding shortest path and detecting bipartite graphs. Topological sorting. Topological sorting arranges the vertices of a directed acyclic graphs in a linear order, helpful for scheduling tasks with dependencies. Shortest path problems. Dijkstra's algorithm, a fundamental algorithm for finding the shortest path between two nodes in a weighted graph. It efficiently explores all possible paths, selecting the one with the lowest total cost. Bellman-Ford algorithm, an alternative to Dijkstra's, useful for graphs with negative edge weights. It iteratively relaxes the distances until no more improvements can be made. A star search, a heuristic based algorithm that estimates the cost to the goal, guiding the search towards most promising paths, widely used in pathfinding and route planning. All pairs shortest paths. Techniques like favored Warshall algorithms that compute the shortest paths between all pairs of nodes in a graph, useful for network analysis and optimization. Minimum spanning trees. Firstly, let's look at the definition. A minimum spanning tree is a subset of the edges of a connected weighted graph that connects all the vertices together with the minimum possible total edge weight. Prim's algorithm. Prim's algorithm is a popular method for finding the MST of a weighted graph. It starts with a single vertex and greedily adds the cheapest available edge until all the vertices are connected. Kruskal's algorithm. Kruskal's algorithm is another widely used technique for MST computation. It sorts the edges by weight and adds them to the MST one by one, avoiding the cycles. And its applications. MSTs have numerous applications in network design, transportation, planning, clustering, and other areas where minimizing cost while maintaining connectivity is crucial. Network flow and applications. Network flow. Analyzing and optimizing the movement of resources, information, or entities through interconnected nodes and pathways are called as network flow. Transportation networks. Modeling and optimizing transportation systems such as traffic flow, airline schedules, and logistic operations. These are the transportation networks. Communication networks. Designing and analyzing the efficient transmission of data through computer networks, telecommunications, and the internet. These are the communication networks. Supply chain optimization. Applying network flow principles to streamline the movement of goods, resources, and information in complex supply chain is called as supply chain operations. Conclusion and future directions. As we explored the fascinating world of graphs and networks, it's clear that this field holds immense potential for unlocking insights and solving complex problems. Moving forward, we envision continued advancements in areas such as machine learning applied to graph analysis, the developments of more efficient algorithms, and the exploration of novel graph-based applications in fields ranging from social networks to transportation systems. The future of graphs and networks is wrapped with possibility, and we are excited to see how this domain will continue to evolve and transform the way we understand and interact with the world around us. By staying at the forefront of these advancements, we can unlock groundbreaking solutions and drive innovation in countless industries.